In many industrial installations where steam is employed, the boilers feed into a common header like this. Steam then flows from the header to the various items of plant, such as dryers, digesters, turbine-driven pumps, and perhaps a turbine generator. In this arrangement, the steam pressure will be relatively low, say 250 to 500 psi. Each boiler is fitted with a non-return or check valve to allow boilers to be floated on or off the header to meet steam demand. Stop valves are fitted in each boiler to permit them to be isolated at times when maintenance is to be performed. Nowadays, it is more likely that an industrial installation will include a back-pressure turbine or pass-out turbine like this. In this case, one single boiler feeds each turbine, and the pressure is likely to be about 1,200 to 1,500 psi. Steam exhausting from the back-pressure unit or extracted from the pass-out unit feeds into the common header, which then supplies the industrial process. Where the plant is devoted to the production of power only, it is normal for each turbine to be supplied from its own individual boiler, so forming an individual boiler turbine generator unit. The main steam circuit is relatively simple, with one line passing from the boiler outlet to the turbine inlet. For a modern power plant, the steam pressure will probably be within the range of 1,800 to 2,800 psi. In order to withstand this high pressure, the walls of the pipework must be thick, perhaps 2 to 3 inches, depending upon the pipe diameter. The steel alloy materials containing chrome and molybdenum are selected to withstand the stresses imposed by the high temperature operation. A thick layer of heat insulation is placed around the pipe to prevent heat loss to atmosphere. Note the valves which are installed in this system. In this particular boiler, we have a stop valve located at the steam exit. In many cases, this valve is omitted and steam passes directly from the boiler down to the turbine's stop valve, which provides the turbine protection by closing automatically in case of a turbine trip. In this module, we'll be looking at the situation in which the boiler stop valve is installed. Once the turbine stop valve is open, steam passes into the steam chest, and from here it is admitted into the turbine through the control valves. During a cold start of this unit, we would need to charge the main steam line from the boiler's stop valve down to the turbine stop valve. However, with steam pressure on one side of the valve at, say, 900 psi and 0 on the other, we would find it quite impossible to open this large valve. To overcome this problem, 1 or 2 small bypass valves are fitted, say 1 inch in diameter. Due to the much smaller face of this valve, it can be opened to allow steam to enter the main steam line. Initially, this steam line will be cold, and the steam will obviously condense. This condensate must be removed through the drain lines, which are fitted at low points on the line, including just before the turbine stop valve. Initially, water will discharge from the open drain lines, but eventually, as the piping warms up, this will turn to vapor as less condensate is produced. The drain valves can then be closed, except the before stop valve drain, which should be left partially open. During this time, the pressure in the pipework should be building to a level equivalent to the boiler pressure and allow the boiler stop valve to be opened. This maneuver cannot be accomplished too quickly, as we must allow time for the pipework to heat at a reasonably unified rate. The whole operation could take as long as 45 minutes or more. A similar procedure must now be adopted to charge the turbine steam chest, that is, by opening the turbine stop valve bypass. We have already discussed this procedure in the module on turbine operation. The most important thing in this maneuver is to make sure that all of the water is discharged from the drain lines to prevent any water from being carried along with the steam and damaging the turbine when we start up. The piping must undergo considerable expansion as its temperature is raised from, say, 200 to 1,000 degrees Fahrenheit. The runoff pipework is designed with deliberate bends and turns to accommodate the expansion between 2 fixed points. that is the boiler outlet and turbine inlet. The pipe hangers and supports are designed to be flexible and allow movement of the pipe under expansion forces. The operator should make himself aware of the normal position of critical pipe hangers. Often an indicating pointer is fitted to allow this. If a hanger does become jammed and prevents the free movement of pipe, physical damage may occur to the pipe itself or to other supports.